Hey guys, so why don't we now recap everything we've learned so far this here week? Notes, areas under curves, and let me jot down something like consider region S. And let me draw a shape for us here. Let's draw something like this here. Let's pretend that this is some function f of x. And let's suppose that we're going from A all the way to B. And we're going to go like straight up like this, all the way to the top, all the way to the, ooh, let's try that again. It's kind of sloppy there. And we'll go from A to B, and the region inside, call that S. And what we are interested in is finding the area of this region. Like when you were younger, they had you guys find areas of things like squares, triangles, rectangles, parallelograms, circles, and so on and so forth, right? You know the formulas for all those shapes, but what kind of shape is this here? It's nothing you've ever seen because it's fluid. It goes up and it goes down and it twists and turns. I don't know what kind of shape this is. So how am I going to find the area of something very unpredictable like this? Well, jot this down. So let's say something like, to find the approximate area of region S. So to find the approximate area of region S, we will use rectangles, period. So this is what we're going to do today. To find approximations, just like a ballpark figure, we're going to use rectangles. Let me also jot this down here for us. To find the exact area of region S, we will use antiderivatives. So here today in this lesson, we'll use rectangles to find like a decent approximation for the area of something that looks like region S. But later on, next week, perhaps, maybe the week after, we'll see, we'll use antiderivatives. We'll do that later. But for now, we're going to use rectangles. So why don't we actually just begin with an example? All right, let's jump straight to an example. So our goal today is to draw pictures like this and to find the area of something like this by using rectangles. So let me clear the screen and let's begin with an example. So example, let's go here. And it's going to say something like use 4 rectangles with, let's say, with left endpoints, to approximate the area below, let's go, f of x equals, how about like 1/3 x squared plus 1 between x equals 2 and x equals 3, period. Jot that down, guys. We want to use 4 rectangles with left endpoints to find the area underneath this curve between 2 and 3. So my recommendation to all the classes so far has been to draw a picture, model the situation if possible. So let's go to the x and y axis. Yes. Let's go something like this here. And specifically like in the first quadrant. Now, what would Desmos say about what this equation looked like? If you were to type in 1/3 x squared plus 1, you know that it would be something like a parabola, right? So why don't I just focus on the parabola, but really like on the first quadrant. So the parabola would look, it would look something like this, right? I'm really only going to focus on the first quadrant. This is the equation for this parabola. That's this guy here, okay? Now, I want to focus between x equals 2 and x equals 3. So let's just pretend that this is 2 And let's pretend that this is 3. It's not drawn to scale, right? The scale is horrible. It's not drawn to be scaled. It's drawn to be convenient. So what I want you to do is at 2, I want you to go straight up until you hit the equation, the function, the graph. There it is. So our goal, don't shade this in. Don't do this, just watch. Our goal is to find this area here, right? This blue stuff, that's the goal, to find this area. That's the goal. Let me just get that out of the way. So that's what we're trying to do, find the area. So here it says 4 rectangles. So if you're going from 2 to 3 and you're supposed to use 4 rectangles that are the same width, exactly how wide should each rectangle be? So here's what we do. Let me create a text box and you guys can jot this down. The width of each rectangle is given by, let me give you guys a little formula. So the width of every rectangle is found by doing this. Let me give you a little formula. And the formula goes delta x equals b minus a over n, where who exactly is a and who exactly is b. So 2 plays the role of a and 3 plays the role of b. And of course, 4, that plays the role of n. Right? So the number of rectangles is n, and then b and a are the endpoints. And then delta x is just the symbol that we use to represent the width of each of these rectangles. So let's actually plug in these numbers. So for this problem, it's going to be 3 minus 2 over 4, which is 1 over 4, right? So that's going to be the width of each rectangle. So now in the picture, from 2 to 3, break it up into 4 sections because there's going to be 4 rectangles. So let's divide this into 4 clusters. 4 sections equally spaced out. And from 2 to 3, the jumps are worth 1/4. So this would be like 2.25. This would be like 2.5, 2.75, and of course 3. So you want to space this out. And why don't you draw those vertical beams going up toward the sky until you hit the curve? So there it is, guys. We have 4 sections. We have 4 compartments. But what we have to do is we have to draw rectangles. So here's the thing. I'm going to draw a rectangle, but I have to use left endpoints. So for example, just follow the cursor with your eyes. Here and here, I'm supposed to draw a rectangle, but should the rectangle be this tall or should it be this tall? Because it's different, right? So because the direction said left endpoints, what you're going to do is you're going to draw from the left like this here in pink. I'm going to draw from the left. And then when I hit the curve, I'm going to go over, and that's 1 rectangle. Let's try this again. With the next rectangle, trace it up from the left, hit the curve, go to the right, and come back down. Let's try this again. The third rectangle, trace the left, hit the curve, come back this way, and shoot back down. And then the fourth and final rectangle, trace the left-hand side, go up to the curve, shoot to the right, and come back down. So we have 4 pink rectangles. And we're going to find the areas of these 4 rectangles. We're going to add those numbers together, and we're going to be finished. And maybe we can do some labels here. Let's pretend that this is called like R1, R2, R3, and R4 for like rectangle 1, rectangle 2, rectangle 3, rectangle 4. So let me create some space here by erasing some stuff. Let me just erase the delta x part. Let me get rid of this part here. So why don't we find these 4 areas together, and then we'll make some comments. We'll go to Desmos, and then we can dismiss here. So for R1, for the first rectangle, I mean, go back to your middle school days. How do you find the area of a rectangle? You go base times height. So looking at this rectangle here, can we agree that the base of this rectangle is 1/4? As a matter of fact, the base for all of these guys is going to be 1/4. So if it's like base times height, this would be 1/4 times, well, that's the base, 1/4, but the height, how much is the height? Well, see, that's the thing. Since I'm using a left endpoint, what I'm going to do is I'm going to use the number 2. I'm not going to use 2.25, not for rectangle 1. I'm talking about rectangle 1. And for this guy, the height of this rectangle is this here in yellow. See that there in yellow? That there, that's the height of that first rectangle. And that there, that is the y coordinate that you get when you plug 2 in for x into your equation. So this is what I'm going to write down. I'm going to write down f of 2. And what does f of 2 represent? That is the y coordinate when you plug 2 in for x. And I want to plug in 2 because I'm using the left bar of rectangle 1. This will make more sense as we go along. What about R2? For rectangle 2, the base is still 1/4 times. Well, what would you think is the height of rectangle 2? Well, for rectangle 2, the height of this guy is going to be whatever this is right here where the cursor is. Now, what is this? This is the y coordinate when you plug in 2.25. So here, I'm going to call this f of 2.25, and so on and so forth. So why don't you just complete your notes? Right, so here, this base would be 1/4, and the height would be f of 2.5. And then for the fourth and final rectangle, I'm going to use 1/4 times f of 2.75. Right, I have 4 rectangles. All of them have a base of 1/4, and they all have different heights. So how exactly do I recommend that you guys do this on Desmos? Here is my recommendation to you on Desmos. On Desmos, you should definitely type in the equation here, right? You want to type in, as a matter of fact, you want to type in f of x equals all of that. That's going to be in box 1. And in box 2, you want to type in all of these guys. But of course, you want to add these as you go along the way. So let me go to Desmos for us, and let me type in the equation, and let me also type in 1/4 f of 2 plus 1/4 f of this plus 1/4 f of this plus 1. Let me type that in for us, and we can fast forward to that part. So guys, take a look at what I've typed in. In the first box, I typed in the function, and that's the purple parabola. Now in box 2, I typed in all of the rectangles added together. I did notice that they all had a base of 1/4, so I took that out to the front. I factored out a 1/4 to the front, and then inside it's just f of 2 plus f of 2.25 all the way to the end. So these are 4 rectangles. These are the 4 heights of the 4 rectangles from the left, and then we multiply by 1/4 because all of them had a 1/4 anyways. And this number here is your final answer. About 2.90625. 2.9. Let's just call it 2.9 as an approximation. So let's go back to our notes, and let's say that it was about 2.9. So here for this example here, the final answer, let's say it's about 2.9 square units. So, and before, I'll make a couple more comments, and then before you guys leave, let's go back to Desmos. Let's make some connections here. We were trying to find the area underneath a shape. But if you notice, let me focus on the picture. Here's the picture there. If you notice that here's the curve, and here's 2 and 3. So we said between 2 and 3. So we want to find this area here. See that? This section that's trapped, I want to find this area. But it's a weird shape because this is a curve. So this method we've done has rectangles. We filled the space with the rectangles, and the approximate area is 2.9 square units. And I want you to see the picture that makes sense. Because look, how many boxes are squeezed in here? Look, I have 1 full box. I have 2 full boxes. And then I have like a portion of a box and a little bit of residue. You see, if you combine this cutoff and this little cutoff, it gives you almost a full box. So I have 1 square unit, 2 square units, and a little bit more, like almost another square, almost 3. This is almost 3 square units, which is why the approximation is like 2.9. See that? So what we do is we're filling this region with shapes that you and I know. We're filling it with rectangles. And then you find the areas of these rectangles and you get a value. But it's not perfect. Watch, go back to your picture. Let's go back to our notes. Notice that in our drawing here, let me pick a color I haven't used yet. Let me use like, let's say like, how about like this sort of dark greenish? Let me fill it in. You see this here? That there, I'm supposed to account for that. But this here, it gets omitted. This here gets omitted. That part, all of these little green parts are getting left behind because the rectangles, it's not a perfect technique. It's an approximation. So the actual area is probably more than 2.9. It's just that these little pockets are left behind using this technique. Now, before you go, let me just ask you guys this. How would this change if in the problem, if instead of, let me erase here where it says left, let me instead just put the word right. What if instead we wanted to do this problem? So let me just say this and then you guys can go. What if I wanted to do this problem for rectangles, but I wanted to use the right endpoints, the right, not the left, but the right. So R1, R2, R3, R4. So go back to R1. Let's say you want to do this with right endpoints. Well, in that case there, can we agree that I still would have had a 1/4 base length? But for the height of R1, if you use right endpoints, can we agree that instead of f of 2, it would have been how much? It would have been f of 2.25, right? 2.25, Mr. Lee, 2.25. What about for the next rectangle, for R2? The height there, instead of 2.25, it would have been 2.5, right? What about for the third rectangle? For the height, you would have plugged in 2.75. And then for the fourth and final rectangle, the base is still 1/4, but the height, it would have been f of 3. You see that? So it turns out that it does matter if you're using left or right endpoints so that you know which values to plug in for x. So that's pretty much what we taught in class. So I recommend that when you guys do this, you make a picture, okay? Make a picture and then find your delta x by going b minus a over n. Make a picture, find your delta x, and then find all the separate rectangles to show all the work by hand, and then go to Desmos and type things into Desmos and just go from there. So if you have any questions, go to the comment section, but if not, see you guys next time. Have a good day.